As an introduction to Chapter 4, I just want to go through some of the overview slides just to kind of go through this initially. But we're really talking about alkanes, which are carbon-carbon bonded compounds. There's a lot of actually things to talk about in terms of the foundation of organic chemistry. So one of the things that we will talk about initially is just kind of their general structure. We have different types of alkanes. We can have acyclic, which means they're not cyclic, or straight chains, and some of them will have branch points off the sides. And we can also have cyclic compounds. We've spoken earlier in the semester about their orientation and their hybridization state, and we've discussed some of the intermolecular forces that can be associated with simply hydrocarbons, which is mostly the weak van der Waals forces. We will discuss naming conventions. Some of those naming conventions are shown here, but we'll go into more detail about those. We'll talk about how these things, when they are lined up, this is kind of showing you different perspective of how these things can line up and be associated with each other in space in these different eclipsed and staggered formations. And we'll talk about that a little bit more. We'll talk about the differences in how that changes the shape and how they are based off of strain and different torsional strain in terms of where things are, steric strain and angular strain. Again, we'll talk about that in more detail. We'll talk about in cyclic conformations, we have different types of ways that those compounds can be oriented in space, and we'll discuss that and where the different elements off of those chains are going to be organized in space, because again, that changes how things are going to interact with our alkanes. We'll discuss the difference between different types of isomers, constitutional isomers versus stereoisomers, and we'll also start to discuss naming, or these different ideas of nomenclature in terms of how to name these different alkane groups and how we get the names for these different elements. We will also discuss this concept of oxidation and reduction with these compounds. So as a starting point, Chapter 4 is all about alkanes, and alkanes are a lot of times these long chains of carbon, and typically those are things that we get these products from a lot of times crude oil. There's a lot of different types of carbon in crude oil, and there are long chains of carbon. And this is kind of what this picture is showing you. It looks like an oil spill, unfortunately, but those are all alkanes that are floating around on the surface of the water. So the problem is the difficulty for cleaning this up is that they're not water soluble. And so it becomes really time consuming and expensive to clean these oil spills up, because this is all non-polar kind of compounds that are very difficult to clean. As you may have noticed in your hood, if you kind of spill some of these compounds, they're not always as simple to clean up and wash up as water compounds might be from previous chemistry classes or biology classes. These are the main types of alkanes, alkenes, and alkynes. So just carbon-based hydrocarbon compounds. We have just single bonded carbons, double bonded carbons, triple bonded carbons, and aromatic compounds, or arenes. So we have these different names associated with them. And when we start to name these, you'll notice that ANE versus ENE, YNES, and aromatic compounds are going to be named a little bit differently. And we'll talk about those names and how we do that in this chapter, for at least for alkanes. So the generic formula for an alkane is CN, so it's any whole number integer. So for every carbon, you have 2N plus 2 hydrogens associated with it. That's going to tell you that you have an alkane. You don't have to memorize this, but essentially what it's telling you is that when you have, for example, 1 carbon, you have 2 times 1 is 2 plus 2, so you'll have 4 hydrogens. And as you increase the number of carbons, that's going to tell you the number of hydrogens you will have. So that means that every carbon is sp3 hybridized, because we have 4 things that are bonded to it. And remember, we have to have those 4 orbitals, that the s and 3p orbitals hybridized into 4 different unique orbitals, and those all have 109.5 degree bond angles. So they are in a tetrahedral shape. Alkanes can be in a straight chain conformation. They also can be in a branch chain conformation. And you'll notice they still have the same number. So these are isomers. We'll have 4 carbons for each of these. And if you count out the hydrogens, you'll have 3 and 6 and 8 and 10. So it will be 3, 6, 9, and 10. So we still have the same number of hydrogens, same number of carbons. They're just organized in a different way. And these are called constitutional isomers. So this is something you should know what the definition is. And it's we have the same number of atoms. They're just organized in a different way. We are going to talk about how we can name these. We name or constitutional isomers in different way. You'll notice this is butane and this is 2-methylpropane. So they have different names. They are distinguished from each other, but they are still constitutional isomers. Here you can see another example of different constitutional isomers: pentane, 2-methylbutane, and 2,2-dimethylpropane. The way in which their atoms are connected to each other are different, but they still have the same number of carbons and hydrogens if you would count them all up. And they do have different unique names, and we're going to talk about how these are named. We can draw these out in different ways. Here's pentane. And you'll notice that these are actually not constitutional isomers. It doesn't matter how we draw those 5 carbons in a row. We can draw them, and this is skeletal structure, and we're going to start using skeletal structure a lot more going forward in class because drawing out each of the individual hydrogens are going to take too long. So in order to increase the ability to kind of cover these concepts, chemists typically use this skeletal structure. And remember, that means there's still 3 hydrogens off of here, and 2 here, 2 here, 2 here, 3 here. We use the same rules. We're just not showing them to simplify this and to be able to name these quicker and more easily, because you're not distracted by the hydrogens floating around, which don't really dictate what the name is. Now, this 5 carbons in a row is still 5 carbons in a row. It doesn't matter if you kind of draw it out like this zigzag, or if you have kind of a half of a hexagon here and then come up, or however you want to draw it. These are still 5 carbons in a row, and these are not constitutional isomers. These are just different ways of drawing the same exact compound. This idea and this ability to recognize that is going to be important for when we start to name these compounds. So now here I've mixed those different ways of the skeletal structure and then kind of the drawn out structure. I want you to redraw C and D in the skeletal form, and that'll help you identify if you think that these are the same thing. So which of the following is not another representation? So which one's different than A or B? And I would like you to draw that out and think about that. And we'll talk about that in class when we come back on Wednesday. For naming these, the first step of naming these alkanes is to identify the longest chain. And the longest chain, again, it doesn't matter how it's drawn out, like the previous few examples. It just matters that you can find the longest continuous chain that doesn't branch off. And here, the way we name that is if we have 1 carbon in the chain, it's a methane. If we have 2, it's ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane, tridecane, tetradecane, pentadecane, icosane. You don't need to memorize all of these. I would say up to 10 would be helpful, because then when we're naming things, then you're able to do that without taking a long time to figure that out. So I would say you will want to memorize these methyl ethyl propyl butyl pentyl up to the decane. And so this is another kind of way that you might want to look at this as just a little more concise and a little bit smaller chart with the same, pretty much same thing. It's just showing you the difference in the names here. These tell you the number of constitutional isomers. So once we get to more complicated structures, we can start to chain. These carbons can chain off into different groups, and we can get really complex structures as we get longer and longer chains of carbon that are able to organize themselves different amongst themselves. So remember, we can have those side chains coming off the more carbons we have. And for example, we go from 2 different constitutional isomers, 3, 5, 9, 18. You start to see this expand exponentially here as we get into larger and larger carbon groups. I want you to draw this down, and again, we'll cover this again when we speak on Wednesday. And I'd like you to draw the 5 constitutional isomers having a molecular formula of C6H14. So how many different ways can you draw this out that are different and unique carbon structures? So bring this with you on class on Wednesday, and we'll talk about the answer. We also can talk about things that form rings. So when we go into cyclopropane, remember the 3 carbon chain is, so we start with methyl is 1, ethyl is 2, propyl is 3. So propane, A-N-E ending, means that it has a single bonds only. There are no double bonds. So the propane would be a straight chain carbon. The cyclopropane is telling us we're in a ring. So cyclopropane, cyclobutane, cyclopentane, cyclohexane. These all have the common feature that the carbon atoms are aligned in a ring structure between them. So we're going to talk about this systematic naming for our organic compounds. The ibuprofen or trade names, you can create these things from, you couldn't necessarily create the compound from the generic name. However, if I give you a systematic name, so this compound, the 2-4-2 methylpropyl phenyl propanoic acid, tells us something about this group. We know that the phenyl group, this is a phenyl functional group. We have a carboxylic acid functional group, that's the propanoic acid. There are different types of things that are told to us about this. The methylpropyl group is up here, and we're going to discuss how we can get this name. If I have this name, I should be able to actually draw this structure, and from the structure I should be able to get the name. So that's the unique systematic way that we do this. We won't probably get into anything this complicated, but we're going to start with a lot more simple compounds, and we'll move up into more complex systems. So there's 3 major parts of naming these compounds. We have the prefix, the what and where are the substituents, the parent chain, which is the longest carbon chain, and that's going to be these groups that I spoke about earlier, and then the suffix, and we'll talk about the functional group. Right now, we're going to focus on alkanes, so they will have the suffix will be the A-N-E ending. The parent chain, remember, is the longest chain that you can count, and we're going to use this as the parent name. So the methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. And then where the substituents are going to go in the front. So kind of the groups that are coming off the chain as different branch points or different things off of that longest chain. So here's an example of naming. We have these compounds, and we're going to find the longest chain. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8, that means that the parent name is going to be octane, A-N-E ending, because there are no double bonds or other functional groups. And we can look at different ways of counting. So if I count 1, 2, 3, 4, 5, 6, 7, that's not as long. So we have to go this way. You don't have to, right? If I were to, you can redraw this in any way. Remember, we talked about that. It doesn't matter which direction that is in. So if I want to draw octane out, 1, 2, 3, 4, 5, 6, 7, 8, I could draw that out. And then on my, usually you're going to number these. On my 2nd carbon, I'm going to have a methyl group coming off. On my 6th carbon, I'm going to have a methyl group coming off. And on my 5th carbon, I have a methyl ethyl group coming off, right? I have 2 carbons. So this is how we're going to start naming these. These are the same thing. These are both okay to draw these out the same way. This is just going to be a different way to orient the carbons, but we still can count the longest chain in both of those are going to be an 8. We can't count it in a way that gives us a shorter than longest chain. So 7 isn't the correct number because it's not the longest chain that we can find in that group. Another rule that we want to look at is if we have an equal number of length in our chain for two different compounds, or these are the same compounds, but we can count number 7 carbons in a row in the same way. If we have the more substituent groups or branched points, is what that is basically telling us. If we can get more of those on the same length of chain, we'll take the compound that has the more substituents off of it, or the more branch points. So these are a couple of different rules for naming these, and we're also going to look at some more examples here where we look at the longest name. The first substituent group should have the lowest number. So we want to make sure that if we're going to number these and identify the different numbers of carbons, we want that first group on the lowest number. So if you read this out from left to right, you'll notice that the first group comes on the second carbon. If we read from right to left and number it, so 1, 2, 3, that first group comes on the 3 carbon. So we're not going to use the higher number. We're going to try to get those numbers to be the lowest possible numbers at all points. If we have the same numbers, so example on the bottom here, we go 1, 2, 3, 4, 5, 6. They both have 6, depending on if we number it from left to right versus right to left. We get the groups will have numbers of 2, 3, and 5 on the left version, and 2, 4, and 5. So what you'll notice is that this is the correct one because these numbers 2, 3, and 5 are lower overall than 2, 4, and 5. So this 4 versus the 3, that's not correct. We want to have the lowest numbers. And again, the point of this is to try to have a systematic way of doing this. So every time you create a compound, you're going to be able to create it from the name, or from the name be able to recreate the compound. And these ambiguities, eliminating these ambiguities, helps us to do that. And the last rule that we're going to talk about is when we're assigning those numbers, and if all other things are equal, we'll always number the things alphabetically with the lower number. So if we have an ethyl group versus a methyl group, so this is a methyl group as a 1 carbon group versus a methyl ethyl, we have an ethyl group here. E comes alphabetically before M, so we're going to give E the lower number than M. So methyl 3 versus ethyl 5, and that's just typically how this is done. So in order to do this, again, we find the longest chain. So in this case, it's 8. We number each of the groups that are branching off points. We have a 2, we have a 5, and we have a 6 branch, and then identify how long those are. So we have a methyl group on 2, methyl group on 6, and we have an ethyl group on the 5 carbon. So you start to identify these different substituent groups, and then we can put these together. If we have multiple groups that are the same, so we have 2 methyl groups, we're going to use dimethyl. If there are 3 of those, trimethyl, tetramethyl, and so on with those Greek prefixes. So at the end, we'll combine the names, and this is the same compound that we saw before with 8 carbons long, substituent groups at 2, 5, and 6, and this would be the 2,6-dimethyl. So we have the 2 and the 6 dimethyl is that grouping off of the side chain. And we have the ethyl group, which we also have to include, the 5-ethyl. So we then put that on in front of the name. So you have dashes between numbers and letters, and then commas between numbers. So here we have the 5-ethyl, which is this group right here, is telling us this group, dash 2,6-dimethyl. So on the 2 and the 6 carbon, we have dimethyl, and then the overall group is an octane. So we have 8 long, octane, ANE ending. So here are some other examples of these groups. And I'd like you to look at those names and identify the long chain, identify the substituent groups, look at the numbering, number those compounds, and see if that makes sense to you. And again, we'll cover this a little more in detail on Wednesday when we meet as a class again.